is Zheng, and he'll talk about the non-invertible symmetry resolved after Ludwig-Cardy formula. Please start.
Okay, thanks for the organizers for organizing this interesting workshop, and thanks for giving me the chance to present the talk. And today I'm going to talk about this non-invertible symmetry resolved after Ludwig-Cardy formula, which I'll explain what that is. And this talk is based on two works in collaboration with amazing collaborators, Icho and Brandon. And the talk is based on these two papers that we put out recently. So related ideas has also appeared in many papers recently. And here's the list of the papers. As you can see that most of them appear almost at the same time. So I'll point out where they overlap with our work. And if you're interested, please take a look at all of these papers. So, okay, so let me start with the motivation. So let's go back to 1986, where Cardy showed that in any 1+1 DCFT, which I will assume to be bosonic, unitary, compact, non-chiral, and with only a single vacuum. So with all of these properties assumed, then the partition function on a circle which is the space manifold with the circumference L, exhibits a universal behavior at a high temperature. So the partition function is like this. So where Q here is -2 pi L over beta, where beta is the inverse temperature. And Cardy showed that if we take the high temperature limit, which means that L is much bigger than beta, then the partition function, which is defined in this way, as 1, QL plus L0 bar minus C over 12, exhibits a universal behavior, which is controlled by the central charge of the CFT. So this works for arbitrary, and there's a subleading term. It works for arbitrary CFT with the property that I assumed. Okay, so using this formula, Cardy derived the asymptotic density of states of the CFT. Now, several years later, Affleck and Ludwig in 91 generalized Cardy's computation to include the boundaries. So in particular, they consider define the CFT instead of on a circle, but on an interval with the choice of the two boundary conditions. And the interval length is L. And for simplicity, let me assume that both the boundary conditions are simple. In the sense that they cannot be decomposed into the sum of other more elementary boundary conditions. And then they also showed that the partition function, also at the high temperature limit, also exhibits a universal behavior, where you define the partition function to be traced over the interval Hilbert space with two boundary conditions, B1 and B2. With this standard factor, then in the high temperature limit, beta smaller than L, then you'll get, apart from the universal behavior that Cardy originally found, there's also a boundary contribution, where G1 and G2 are now called the G functions, coming from each boundaries. Okay, so this asymptotic, so this high temperature behavior, universal behavior of the partition function in the high temperature is not only of theoretical interest, but it's also related to the entanglement. So let me briefly review how the entanglement is related to this universal behavior of the CFT partition function on interval. So let's consider entanglement entropy. And in order to compute the entanglement entropy, we just usually we take the CFT and we take the ground state, and we bipartite the system into two parts. Where into region A and the region A bar. And then we compute the reduced density matrix by tracing over the degree of freedom, tracing over the Hilbert space in the region A bar and to derive the reduced density matrix of region A. However, this requires, so in order to trace over the Hilbert space of the region A bar, you have to define what is the Hilbert space that is localized at the region A bar. But typically, generically, the Hilbert space does not decompose under the decomposition of these regions. So which means that you have to specify some conditions, boundary conditions, which has been nicely discussed in paper by Kantaro and Yuji 10 years ago. Where they treated this boundary condition very carefully by assigning some small regions, which is of the size epsilon. And if you take the epsilon to be very small, then the size of the interval, then you will get two boundary conditions, which we denoted by this B1 and B2. And the reduced density matrix then depends on the choice of the boundary conditions. And they also showed that using the conformal map, this reduced density matrix is related to the CFT partition function on the interval with the choice, with the given boundary condition at the entanglement cut. Okay. So this relates how the entanglement. So this relates the reduced density matrix with the data in the CFT on interval. And then from this reduced density matrix, then you can, it's standard to compute the entanglement entropy using this reduced density matrix. And oh, by the way, this Q here is related to this length L and size epsilon in this form. And what is important from this expression is that the L is greater than epsilon. This limit precisely corresponds to the high temperature limit of the CFT after the conformal mapping. So this is precisely the limit where the entanglement entropy, we usually consider the entanglement entropy, we usually take the size of this interval to be large compared to any other arbitrary scale. And then we can use, so then we can plug into the asymptotic behavior of this CFT partition function on interval. So let me write down one more step. The entanglement entropy is usually computed for convenience as the n equals to 1 limit of the Riemann entropy. And this guy taking the trace can be explicitly written in terms of the partition function of the CFT on interval as B1, B2. So now it's straightforward to plug in into this universal behavior of the CFT partition function into the expression for time entropy, and you'll get the standard leading terms, leading contributions, C over 3 times log of the interval size times plus the boundary contribution. This is the log of this. It's usually called the boundary entropy. Okay. So this is very useful because as so many condensed matter physicists usually want to consider in time entropy, and it's even measurable experimentally. So it's nice to see that there's a connection between this universal behavior of the CFT partition function and the in time entropy. Okay. Now, yes. Yeah. That's right. That's right. So if you if you consider one single system with a choice of this regularization or the boundary, then the subleading term seems to be meaningless because it depends on like how you regularize. But if you have two systems and we choose the same regularization and we compare them, then it's meaningful. Okay, now let me switch gear to another motivation, which is the symmetries. So it's well known that well known by now that in 1+1B CFTs, many CFTs enjoy many interesting global symmetries, the generalized notion of the global symmetries, and in particular non-invertible symmetries. So it enjoys a zoo of non-invertible symmetries. And usually when we have a symmetry, we can use them to organize the states and operators into different multiplets or different sectors or different representations. And because this is usually what we do for the ordinary symmetry, but now we have a more generalized symmetry, so we should be able to do the same. Okay, so now then it's natural to ask, like, what happens? Okay, so if you have a symmetry, as I said, you have a Hilbert, so you can decompose the Hilbert space into a direct sum of the Hilbert space, where each sub-Hilbert space corresponds to each single individual representation, and you can sum over the representations. So you can decompose into you can decompose the whole Hilbert space into sub-Hilbert space according to the representations. Now, because the Hilbert space can be decomposed or can be refined or into sub-Hilbert spaces, then we can ask a more refined question, like, what if we compute the trace of the Hilbert space but within a fixed subsector, within a fixed representation rho? So on S1, so on S1, let me see. Yeah, this has been, so we can ask, like whether there is a symmetry or non-invertible symmetry resolved Cardi formula, or in other words, this universal behavior of the partition function on S1. And yeah, so you just take the trace over the S1 Hilbert space with the fixed representation, and you weighted the sum by the standard phase factor of the factor. And this problem has been systematically discussed recently by very nice papers. Sun from the 20s, and Lin Sifnashi and Tachikawa. And they derived the universal behavior of leading behavior of this partition function at high temperature, and they found some additional, some new contributions at the subleading order. Okay, now the goal of this talk, or the focus of this talk, is to, instead of considering the partition function on the S1 on a circle, but we consider the theory on an interval. And we ask similar questions. So on interval, then we can also decompose the Hilbert space, but with a choice of boundary conditions into different multiplet representations. And we derived the analog of this Affleck. Oh, by the way, I'm going to call this formula the Affleck Ludwig-Carty formula. So I'm going to derive the symmetry resolved version of this Affleck Ludwig-Carty formula. And once we have this, then we can easily, by plugging into this expression, to get the symmetry resolved version of the entanglement entropy. Okay. And symmetry resolved entanglement entropy is actually has been discussed quite frequently. And actually, this symmetry resolved entanglement entropy was first motivated by the experiment, and then series like jumps into the field and try to compute, do some various generalizations. So the upshot is that this quantity is not only of theoretical interest, but also experimental interest. Okay, now the goal of the talk is to derive the symmetry resolved version of the Affleck Ludwig-Carty formula. Namely, we want to compute this partition function. In the high temperature limit. But before discussing that, there are several things that we have to first clarify. So we haven't defined what do we mean by the representation of the non-invertible symmetry on interval. So there are several questions that we want to ask before we do the computation. The first question is, so before talking about representation, we know that representation is the representation of algebra. So we need to figure out specify what is the algebra that we are talking about. So for given boundary conditions, how the symmetry operator acts on the interval Hilbert space. And we want to figure out the algebra formed by these operators of these operators. And the second question is, now we know the algebra, then we want to ask what is the representation or irreducible representation of the algebra. And third, once we know the representation, or once we have defined what this representation is, then we want to construct this sub-Hilbert space for a given representation. So how to construct it? Or in other words, or equivalently, we can construct the projector, which projects the total Hilbert space on an interval into this sub-Hilbert space. So these are the same questions. So in the rest of the talk, I'm going to answer these three questions and then derive the symmetry result after Ludwig-Carty formula for the invertible symmetry first, and then for the non-invertible symmetries. So, okay, so as a warm-up, let's first talk about the invertible symmetries. So invertible symmetry G, and for simplicity, I'm going to choose the two boundary conditions to be identical. Of course, we can choose the boundary condition to be different, but that's more complicated. So let me, as a warm-up, let's just be as simple as possible. So we choose the same boundary conditions. Now, what is the answer to the first question? So first of all, we want to consider the symmetry that are acting within a Hilbert space for given boundary conditions. And we assume that the boundary condition is simple. So it means that the symmetry operator should map the Hilbert space to itself, which further means that the boundary condition should be symmetric, G-symmetric. And then because the boundary condition is G-symmetric, so we can, the fusion of the two symmetry operators just obey the ordinary group-like fusion rule, as if there's no boundary. So this is the answer to the first question, which is that the algebra is just a group algebra. Oh, by the way, I'm only going to consider the finite symmetries in this talk. Now, how about the second question? Well, because the algebra is the same as the ordinary group algebra, so the representation is just a linear representation of the group. You can see, as you can see, that the reason that I want to focus on the case when the two boundary conditions are the same is because if the two boundary conditions are different, then the representation can be a projective representation. But later in the more general treatment, I'm going to include those projective representation as well. Now, then for the third question, what is the Hilbert space for the given representation, or namely how to construct the projection operators? Well, this projection operator is also known in the literature, which is given by this formula, where this chi is the group character, and this is just is an operator that acts on the interval. And from this expression, then you can explicitly check that it satisfies every desired property of the projector. For example, you can check that P rho prime equals to delta rho prime P rho, which is essentially the only thing you want to check, because this is by definition, this is a projector. Multiplicity. So what multiplicity do you want? Yes, but yes, well, yes, then it's the reducible representation, right? If you consider several copies of the irreducible representation, then it's reducible. Yes. Yes, the whole Hilbert space. Yes. Yes, yes, yeah, that's right, yes. Okay. Now we have answered all of the three questions in the simple case of the group. Then we can proceed to compute the symmetry resolved artificial Ludwig-Carty formula. Yes.
There are boundary condition, for example, periodic or boundary fixed.
No, so the only thing I'm assuming is that the boundary conditions are simple. It can all, and also symmetric, G-symmetric. So as we said here, the boundary condition is G-symmetric, so that the symmetry operator can terminate topologically on the boundary condition. I'm considering the system on an interval, so it's not periodic. Okay, so now since we have already answered the three questions, then we can proceed to compute this symmetry resolved after the Ludwig-Carty formula. So let me send details. So we want to compute this trace on the Hilbert space with the same boundary conditions with a representation rho weighted by this standard factor. And by definition, this is equal to the trace of the full Hilbert space, but with the projector inserted. And we just computed this trace. And then we can plug in to the expression for the projector, so which will reduce the formula to this. Let me use H I rho inverse trace of H and H huge. Where H hat is just an operator that extending between the two boundaries. So pictorially, we can just draw this diagram where you have an H symmetry operator that connecting the two boundaries, and the past and the future are connected because we assume the finite temperature. So this length is beta, this length is L. And then the standard trick to use is that we rotate, so we can rotate this figure by 90 degrees, namely do a modular transformation. And then this picture becomes this picture, where now it's in the closed string, channel, where the two boundary conditions become the initial and the final state, boundary state, the Carty state. And the whole thing, so this guy can be evaluated in this way. And then if you want to consider high temperature limit, then we only need to consider the leading behavior, which is well known. Oh, by the way, this is the twisted Carty state, twisted by the symmetry operator H. And the leading behavior comes from the Carty state with zero twist. So okay, so let's see. Yes, the behavior comes from the Carty state with zero state. So H1. And then you will get the standard G functions. But because we have chosen the two boundary conditions to be the same, so these G functions coming from the two boundaries are the same. And we have the standard leading behavior of the partition function. Okay. Now, because the leading behavior only comes from the untwisted sector, namely h equals to 1, so we can set this h equal to 1, and this sum is trivial. So the high temperature limit is now just the d rho over g times and the h equals to 1 contribution, which is a chi of identity, which itself is the dimension of the representation times the g functions times the standard Ricardius factor. Okay, and these together give us d rho squared over g. So this is the this is the new contribution that comes from the symmetry resolution. Delta H1. So now if you want to sum over all the H, you want the leading behavior, and leading behavior comes from the sector with H equals to identity. Otherwise, this guy will give a greater than 0 conformal weight, conformal dimension. Yeah. No, this is a leading, and this is the rest are the subleading.
But the leading correction, the leading answer is no. I thought you wanted to go beyond.
No, this is, well, okay, so I'm not sure whether I should, so leading answer is this guy. It's no. G1 times G2, well, G1, I would say G1 times G2 is the subleading contribution that comes on the boundary. And this is also a subleading contribution, which is of the same order as the G1, G2, which is just a constant. Yeah. Yes. That's... Okay. So this is the new contribution apart from the boundary G function. So which comes from the symmetry resolution. And if you sum over the representation, then this factor goes away because the sum of the representation of the d rho squared equals to G, the volume of the G. Yeah, G, I'm only going to assume G is finite. But, oh, by the way, so this computation has been done in the paper by, just a moment, by Suki. And in this paper, they also discussed various other case situations. So for example, when G is a continuous symmetry. Okay. Okay. Okay, so now this is okay. So now we have, so this is the after the Ricardi formula with symmetry resolution, symmetry resolved after the Ludwig-Ricardi formula. And now since you have this, then you can directly plug it into the formula for the entire entropy, and you will get this contribution. So you will get a new contribution coming from the symmetry resolution of the entire entropy. So this is the leading piece. And then you have the boundary entropies. And then you have also another constant piece, which is the symmetry resolution. Yes.
Just general question. The boundary sectors, are there examples for no?
Yeah, there are. Yes, in some cases, for example, for the RCFT, I think it is, Yes, so by the way, do you want to find the further subleading corrections to this? Yeah, yes, yeah, sure. But if you want to consider further leading self-correction, then. Okay. Yes. Now, okay, so this is the warm up. So this is in time entropy, and you found this new contribution. Okay, so now let's generalize the all this discussion to the case of the non-invertible symmetry. This is smaller than 1, yes. So it decreases smaller than 0, yes. So it decreases the intent. Okay, so for general, so now let's consider general fusion category symmetry C. Now, again, we have to answer these 3 questions. So yeah, so we want to, our goal is to compute this. And in order to compute this, we need to answer those 3 questions. So the first question, so what is how does the non-invertible symmetry act on the state on an interval? Okay, so now you want to consider an interval, Hilbert space, and you want to consider the symmetry operator that is parallel to the space direction and acts on the state. So let's call it the symmetry operator labeled by A. And it also comes with the 2 junction operators, x1, x2, and we have b1, 2. In general, this symmetry operator, when it intersects with the boundaries, it will change the boundary condition from b1 to b1 prime and b2 to b2 prime. Yeah. And moreover, the junction space, because the symmetry operators are non-invertible in general, the junction space can be dimension greater than 1. So we really have to keep track of these junction spaces. And then the symmetry operator. So in this case, the symmetry operator will maps. So let's call the symmetry, denote this symmetry operator to be A, which also comes with the other labels x1, x2, and also depends on the choice of the boundary condition, but let's label the symmetry operator by, to be simple, so let's just label the symmetry operator by h of A, which, yeah, because this is an H shape. So I'm going to call it symmetry operator H. And then this H operator maps the Hilbert space of B1, B2 to H, B1 prime, B2 prime. So in general, the symmetry operator that on the interval will map the state belonging to one Hilbert space to another Hilbert space. And if you assume the conformal symmetry, then we can use the state operator correspondence, or you use the conformal transformation to map this geometry, the interval geometry, to the upper half plane. And then the state is mapped to a boundary changing operator. And the operator becomes this semicircle. And then how the state acts on the boundary changing operator. Oh, so here, the state acts on the symmetry operator acts on the state on the interval. And here, by state operator correspondence, and the symmetry operator acts on the boundary changing operator. Yes.
The existence of symmetry, right?
Yes.
And usually we say that symmetry when the symmetry operator commute with the Hamiltonian.
Yes. Yes.
But still, you assume that the Hilbert space changing under the action of the.
Yes.
That
yes.
is not inconsistent. Those are not.
Well, I'm going to say that later. Yes, I'm going to discuss that later. So Now, symmetry operator acting on this boundary changing operator just amounts to like you shrink this symmetry operator, and it becomes another boundary changing operator becomes another pair B1 prime and B2 prime. So yeah, and this is called what we call the boundary lasso action, and this name mimics the ordinary lasso action if you consider how the symmetry acts on the local operator in the bulk. So this is called a boundary lasso action. So in short, the symmetry operator acting on the state on the interval file boundary lasso action. Now, because we eventually want to take the trace of the state within a fixed boundary conditions. So we don't want the symmetry operator to map one boundary condition to another. So, and because we want to consider this a simple boundary condition, if you assume, if you are allowed to consider more general non-simple boundary condition, then the situation can be more general. But now, suppose we only consider a simple boundary condition, then we should demand that B1 equals to B1 prime and B2 equals to B2 prime. In other words, the symmetry operator can terminate topologically on the single boundary. So what does it mean? It means that the symmetry operator or the boundary condition is a weakly symmetric boundary condition in the sense of the paper by Icho, Brandon, Shuhen, and Yang. Right? So this symmetry operator, so the boundary condition. If you want to compute this symmetry resolved after Ludwig-Cardy, by assuming the simple boundary conditions, then the boundary condition should be weakly symmetric. Now, okay. Okay, so now we have known that how the symmetry operator acts on the interval Hilbert space. Then we can further ask like what is the algebra formed by composition of these symmetry operators? Now, so the boundary lasso action, which we denote as whose element is generated by HB, which can be written diagrammatically just as this. So we have two boundary conditions, and both A and B can topologically terminate on this boundary condition B1 and B2. And then how to compute this diagram? We just do various topological moves, right? So for example, we can use the boundary F move. So let's recall what is the boundary F move. Sum of C with some other indices, and this is called F tilde usually. See, and I have suppressed the label of the junctions, but in general, they were non-trivial labels of the junctions. But schematically, this is the boundary move. So using this boundary F move, then you can simplify this expression into this. So this is a B, A, C, C prime, and These are two boundary conditions. And then you can further shrink the bubble. And by shrinking the bubble, you will get some additional factors that depends on the quantum dimensions. So let's call, and then you sum over many things. And after you shrink the bubble, then you will get 2F moves plus some factor that depend on the quantum dimension. And you will get this C. And this is nothing but the edges of C. So comparing the here, the beginning and the end, you see that the composition of the two symmetry operators, the multiplication of the two symmetry operators acting on the interval, is the weighted sum of weighted sum of the symmetry operators on the interval. But this coefficient can be very generic. Unlike the ordinary fusion rule for in the fusion category, this coefficient can be in general non-integer and even negative. And one example of such a composition rule of the symmetry operator on the interval is when you consider the Fibonacci fusion category, where there are two generators, two objects of the Fibonacci fusion category, and you can consider the boundary condition, which is the weakly symmetric boundary condition that can topologically terminate this non-trivial line W. And then you can consider the fusion of the two W operators, and it will give you the identity element here plus the golden ratio to some power. So indeed, you see that these factors come from the computation of this fusion boundary moves and this depending on these numbers. So indeed, this number is not integer. Okay, so this and in general, here we have explained that how the different elements of the symmetry operator on the interval can compose and multiply, and they form an algebra, and this algebra takes this complicated form, and this algebra is called the boundary tube algebra. Okay. And further, if you want to if you are more comfortable with the operators in this picture, so you can do the state operator correspondence, and then the algebra, the boundary tube algebra, is just that if you can consider the fusion, like this rainbow fusion of two symmetry elements, then you will give you F tilde lambda times this action, boundary lasso action. Okay.
Excuse me.
Yes.
Is this algebra associative if you restrict the boundary condition to be the single? In the Fibonacci case, if you restrict the boundary condition to be just W, and then is it associative?
Is it associative? I'm not sure. In general, I don't expect this boundary tube algebra to be associative. Sorry, it's associative. Yeah, I'm not sure.
Associative means.
What I mean is that they are not necessarily commutative.
I'm asking about associativity.
Maybe yes. Yeah, I think.
Okay.
In general, algebra is always associative, right?
I mean,
they're talk about the algebra.
So you think it's associative?
Yeah, I think it's also.
Okay.
But let me
not
make the claim.
Okay.
Okay, good. Okay, so this is the answer to the first question. So in short, and the symmetry operator acts on the interval using via this boundary lasso action, and the algebra of this operator, namely the boundary lasso action, forms the boundary tube algebra. So this is the one sentence summary of all of these discussions. Okay, now sorry, is it overtime now?
You have 8 minutes.
Oh, sorry. Okay, good. Okay, so now let's further proceed to the second question, which is what is the representation of the boundary tube algebra? Okay, so in order to answer this question, we have to. So it turns out to be that it's more convenient to go to use the formalism of the symmetry TFT. Why is the reason? Why is that? Because, well, symmetry TFT has already been proved to be useful in discussing, in characterizing the representation of the bulk tube algebra. So our task now is to generalize the ordinary symmetry TFT construction to include the boundary conditions and to characterize the representation of the boundary tube algebra. Okay, so now let me briefly review what is the symmetry TFT construction. So if you have a 1+1 dimensional CFT, let's assume the CFT, and the same TFT construction is that you can blow it up and this 1+1D series into a sandwich of the 2+1D series. So in the middle, you have a symmetry TFT, and you have this topological boundary condition on the left, which is the Dirichlet boundary condition, where the symmetry operator lives, can live on this boundary condition. And then on the right, you have the dynamical boundary condition, which encodes all the dynamical information. The nice thing about this construction is that it decouples all the symmetry universal information from the dynamics, and the universal information are encoded in the middle and on the and left boundary conditions. Now, we want to consider the boundary condition of the 1+1D QFT. So now we further include the boundary condition here. So let's call the boundary condition B. And now the CFT is the boundary CFT. Now, if you further blow it up into a sandwich, then we have to cap this this sandwich off by another boundary condition. But because the lore, or because the spirit of the symmetry TFT construction is that we want to decouple all the universal information from dynamical one in where all the things in the middle and on the left are topological. So the thing on the top should also better be topological. So this is the topological boundary condition. Let's call it the capital B to distinguish from this B. So this is the bold B phase, and this is the ordinary B. And this topological boundary condition intersects with this Dirichlet boundary condition by a topological boundary condition changing operator. Let's call it the underline B. And this is another boundary changing operator, which is in general non-topological boundary changing operator. Okay, so now what is the meaning of this top topological boundary condition? The meaning of top topological boundary condition can be seen as follows. So we know that the boundary condition for the CFT transforms under the symmetry by parallel fusion, and they form the non-negative integer matrix representation. Now, because here in this setup, the symmetry operator only localizes on the left boundary condition. Therefore, under the parallel fusion of the symmetry operator, only this boundary changing line operator, B underline B, changes. And the top topological boundary condition does not change. Therefore, it's naturally labels the different representations of the non-negative integer matrix representation of the boundary condition. Okay, so in short, this guy labels the NIM reps under the parallel fusion of the boundary of the symmetry operator with the boundary conditions. Okay. Now, this is not what we want. This is not the setup what we want, because we want two boundary conditions. We want an interval. Therefore, and by state operator correspondence, the two boundary conditions can be constructed in this way. So you have, and here we have, so you have B1 and B2, and there's a boundary changing operator. So, and if we further blow it up using the sandwich construction, then we have underline B1, underline B2, and bold B1, bold B2. And there's a topological boundary changing operator, which I'll call rho. And the reason I label this boundary changing operator as a rho is precisely because this boundary changing operator labels the representation of the boundary, how the boundary changing operator transform under the boundary tube algebra, the boundary lasso action. So let me be more precise. So first of all, we know that, as we have discussed upstairs, that this boundary changing operator is acted upon by the boundary lasso action, and the algebra formed by the boundary lasso action is the boundary tube algebra. And because all the symmetry operators, all the boundary lasso actions are localized on this Dirichlet boundary condition, therefore it does not change this boundary changing operator in the middle rho. Therefore, this rho and the topological boundary changing line operator rho naturally labels the different representations of this boundary tube algebra. Just as this topological boundary conditions B1 and B2 labels the non-negative integer matrix representation. So the upshot is that the rho labels is in one-to-one correspondence with the representation of boundary tube algebra. And if we assume that this rho is a simple boundary changing line operator, then this is the irreducible representation. Okay, so now we have answered the second question, which is that this irreducible representation is easy to see in this sandwich setup as the boundary changing operator of the two between the two topological boundary conditions of the symmetry TFT. Okay, so then let's proceed to the third question. We already know that rho labels the irreducible representation of the boundary tube algebra. Then we want to construct a projector that projects onto this rho. Namely, we want to, given a system, we want to find an operator which projects onto a given rho operator if we do the sandwich construction. So then this projector, it turns out, can be explicitly constructed by using what's so-called the half-linking matrix. Yeah, I'm not going to discuss in detail what is the half-linking matrix, but it is just some symbol. You can think of it as a square root of the modular S matrix, which you are familiar with, and the projector can be constructed by the half-linking matrix. So what it means is that if you start with arbitrary, so you have two boundary conditions, B1 and B2, and if you start with the arbitrary representation of this boundary changing operator, then you can insert a bulk line, mu, which is the line in the symmetry TFT. And if you sum over mu, with some other indices, for example, the junction of the mu of this bulk line with the topological boundary conditions, weighted by the dimension of this line and the half-linking matrix, you will get almost what you want, which is the precisely the boundary this rho as the boundary changing operator. So this is precise. This is almost like the projector, right? But the problem of this equation or problem of this operator is that it does not act on the desired Hilbert space. So in order to construct the desired operator projector onto this interval Hilbert space, we want to move these operators, the bulk lines, onto this topological boundary. And after doing such a move, you will find you'll find this configuration, and there will be additional factors coming from these topological moves, which is BP1, 2. These are the dimensions, quantum dimensions of these topological boundary changing operators, together with some additional more contributions of the half-linking matrices. And okay. And this is the projector that you want. Now we have the explicit expression for the projector. Then we can just plug into the partition function that we want to compute, and yeah. So and then okay. And then you can directly plug into that expression for the projector, just as what you did for the invertible symmetry case. And what you'll get is just this. And then you do the standard trick as do the modular transformation and extract the leading behavior or subleading behavior, and which will pick up A equals to 1 channel, and you will get the standard. So this factor coming from here, the standard G boundary G action, the standard Cardi contribution, and some other contribution that come from this half-linking matrices. But as you may anticipate it, that this expression looks very similar as the Felinti formula. In the Felinti formula, we have this fusion matrix equals to S over S. But here, because we are talking about the boundary case, then this S is so the S in the numerators are replaced by the half-linking matrix, as I briefly alluded to. And then the denominator is basically the square root of this S. But it can, so this just has some intuition, but you can show explicitly that this is precisely some fusion. This is precisely an integer which corresponds to the fusion matrix, fusion coefficient of the 3 boundary changing operators. So what are the 3 boundary changing line operators? which is precisely this line, and this line. And this n, they just labels the dimension of this topological boundary changing junctions. So this n is just a dimension of this topological junction between three topological boundary changing lines. Okay, so this is just some integer, which let me call the n with some indices. And then this is we finally get the final result, which is the symmetry resolved version of the Ludwig-Carty formula, where this contribution together with this contribution come from the symmetry resolution, and these are the known contributions. And if you restrict it to the invertible case, you will explicitly see that this together with this reduces to the standard factor d rho square over volume of G, which is a consistent check. And then you can plug in, so this is the universal high temperature behavior of the Petrosian function. Then you can explicitly plug into the expression for the symmetry resolved in thermal entropy, and you'll find the universal subleading behavior. Okay, yeah, I think that's it. So there's a final remark, which is that this setup of the symmetry TFT together with the boundary conditions can be further generalized to the case where you consider the intervals or the intervals, not only the boundary condition, but the intervals. And you can also consider the defects. And by considering this generalization, then it allows you to derive some easy theorems like when the defect can be screened or not. And then this construction can also be used to discuss the anomaly in flow for the non-invertible symmetry, which has been nicely discussed by in a recent paper by Inamura and Oyama recently. And it will also be interesting to generalize this discussion to higher dimension, because here we only discuss 1+1D setup. Yeah, that's all. Thank you very much.
Thanks, Yunchen, for very nice talk. Is there any question?
Can you explain again? It was too fast at the end.
Yeah.
This integer,
Mhm.
the junction, the dimension
Mhm.
of the junction. Can you say which junction is it?
The junction, so it's this junction. It's this junction. So this is a topological topological line operator between these two topological boundary conditions. There are three topological boundary conditions: this one, and the Dirichlet one.
Is there a way to phrase the answer in terms of purely 1+1 without using SymTFT? What are these objects?
Well, you mean this? So okay. Yeah, I don't know. So this object labels the space of the boundary conditions that are related by the symmetry transformation, and this topological surface labels the multiplet of the boundary conditions, and this topological line labels the representation. So labels the representation on the boundary tube algebra of the boundary changing operator. So yeah, it is not, it may not, it's not very.
Any other questions?
Is the boundary tube algebra just factorization homology over the interval, or is it known?
Sorry, boundary tube algebra is what?
Factorization homology over the interval? Is it known if you can think in that
this
term?
language is beyond me, sorry.
Okay.
Yeah.
Any other questions? Okay, if not, let's thanks speak again.
Thank you.